Okay, I'll be talking about tester first, and then I'll show you the very natural connection to streaming algorithm. Okay, so I'll first review the basic definition of what is an epsilon tester. Okay, and then what is a testable property in general. Then the plan is to first study a very famous tester, which is a tester for linearity function, linear function. Tester. Okay, so that's something that is quite well known, and maybe you heard about it, and but then the idea is to actually prove through the Fourier analysis, actually the discrete Fourier analysis, the basic property of the tester. And this is quite interesting in itself. In particular, if you are interested in logic, here, after all, we are in an institute for mathematical logic, and there is a way to push the discrete Fourier analysis to the standard Fourier analysis on continuous function through infinitesimal, through non-standard analysis. So this is in itself quite a subject. So that's the first goal, and I think it should take us about an hour to do it. Then my plan is to move to tester on words. So we will see how to test, for example, regular properties of words with some simple test. And then we'll move to, so first regular properties. And then something which is slightly more difficult is the subset of the context-free properties of words, which is usually called visual push-down languages. And this is very computer science subject. So we'll see what's interesting about this. And the interesting thing is that when we go to streaming algorithms, which is a third subject, essentially any tester, for example a tester for regular properties, it translates automatically to a streaming algorithm using the technique which is called reservoir sampling. But then, to test, there is a way to test far more efficiently VPL languages through what is called streaming tester. In other words, if you look at streaming data, somehow there is a way to distinguish a classical tester which knows the whole data from a tester that knows the stream. Only the stream. And knowing only the stream is actually an advantage, which is a little bit counterintuitive. Okay, so that's what I plan to do. And if I have time, I will move to more practical application, which are streaming algorithm on the graph. Okay. So the basic subject is, let's say this is more advanced, and if I run out of time, I have slides for this and that, and somehow that's maybe a better technique. but let's do by, the classical technique first, the definition of a tester, and then do the linear tester with the Fourier analysis. Okay, so these are, maybe you've seen this already, maybe you haven't. So that's a program. Okay, now if you really, we'll have a pause at some point, at midpoint, and if you really want to hear about a streaming algorithm on graph as opposed to words, just say so, and maybe we'll go there first. Okay, so so what is the motivation for having an epsilon tester? So here, epsilon is a constant between 0 and 1. Okay, and before we go into what we call an epsilon tester, we first need a few notions. So first of all, I need a distance between the various objects. So if I'm talking about words, I need a distance between two words. If I'm talking about trees, I need a distance between two trees. If I'm talking about graphs, I need a distance between two graphs. Okay? And so which distance do you take? Now it turns out it's very important, and if you change the distance, then you change the game and everything changes. Okay, so typically what people first consider as a distance between two words, a binary words, is a Hamming distance. Okay, if the word have the same length. Okay, so Hamming distance is a proportion of letters where you differ. Okay, but then it's not, Hamming distance is one distance, okay? But then you have another distance which is very much used in computer science, which is the edit distance. And it's smaller because you have more operation to match one word with another, because you allow erasing a letter or inserting a letter as opposed to just switching a letter. Okay? So for example, what is the distance between, let's say, for example, okay. So if here two words. Okay, so if you're talking about Hamming, they differ almost everywhere. Not quite. Let's see. That's not what I wanted. Okay. So they differ almost everywhere except one position where they agree. Okay. So how many letters do I have? 1, 2, 3, 4, 5, 6, 7. Okay. So you only reason in terms of relative distances. So this would be this would be 1 minus 1/7. Okay, so in other words, the distance is large, right? They disagree on 6 positions out of 7. All right. Now, if you allow edit, you can the distance is smaller. And why? Because all you have to do is to insert an A here, that costs 1, and erase the last one. So the letter, this time the distance will be 2/7. Okay? And there are a whole bunch of distances that are even smaller, because once you have edit operation, you can have, for example, cut and paste, more complex situations, and the distance will go down. Okay? Well, let's concentrate on this distance. Just edit. Okay, the advantage of edit is that it generalizes to trees. Okay, so editing a tree means removing edges of the trees. So in this case, a tree merges into smaller trees, so inserting an edge into a tree. And it also goes for graphs, where you look at essentially the number of edges you have to add or remove to transform one graph into another. Okay, so for us, unless I say otherwise, we adopt edit. Okay?
So when speaking about graphs and trees, do you assume that the nodes are labeled?
I don't. That's important. So in other words, asking if two graphs are distance 0 is essentially asking if the graphs are isomorphic, which is hard. Okay? So here comes something which is peculiar, and actually you can see it already for distances on words. Sometimes it's very hard to ask, what is the distance between two objects? Okay? That can be hard. Okay? For example, if here I mentioned this last distances, which is called distance with moves. Okay, so what you add is edit, and then you also add this cut and paste operation. So you take a subword, you move it somewhere else. Okay, so for example, if I go back to this word, I could say, well, this subword, I move it at the end, that cost me 1. If you do this, this becomes NP hard to compute the distance. Okay, it's actually worse than a graph in terms of difficulty of asking the distance. But the miracle is that when we're going to look at tester with this distance, algorithm becomes easier. Okay? So that's the catch. All right, so what is now, so this is
distance, a new distance with index m.
This?
Yes.
So it's a minimum number of operations which include modifying a letter, inserting a letter, removing a letter, and making a move. Making a move means selecting a subword and moving it somewhere else. Okay? If you're on a tree, it's the same thing. It's taking a subtree, moving it in one shot somewhere else. Okay? Very useful operation. So once you have a distance now, and then you have a class of words, what is the distance between C, which is a class of word, and W, so that's a definition. This is a minimum over W prime in C of the distance between W and W prime. Okay? So in other words, if I take the set of all the words, so on an alphabet sigma, I take a class or property, so property of words or class for me, it's the same thing. So C, okay? And so here are all the words that satisfy the class. So if I have a word here, what's the distance from W to C? Essentially, you have to locate this W prime so that the distance is the smallest. Okay? And that's a definition. All right. Okay, so that's the first part. Now we have a game with distances between objects. Okay. Now comes the second part, which is the queries. Okay. So what is a query on a word? Well, on a word is that I fix a position on, say, I position, and I ask you what is the letter in position I. Okay? W sub I. Okay, and that costs 1. So the cost of a query is 1. Okay, independent of I. All right? So you have a word of a size 1 billion. You ask, okay, one position, give me the value of the word. It gives you in one step. Actually, if you want the value in position I plus 1, okay, either you count it as another step, or it costs the same, but it depends. Okay, that's a question. If you're on a tree, essentially you take a node, you have a way to label first node, second node of the tree, and you ask, well, what is the label on the ith target, on the ith node of the tree. Now, if you have a graph, for example, so here the situation gets more complicated, and it splits into two. Either the graph is dense or it's sparse. Well, let's suppose we have dense graphs. Okay, dense graph means the proportion of edges is bigger than alpha, the domain square. Okay. Now, if I have a dense graph, then essentially I take random nodes of the set of vertices with a uniform distribution, and I consider the random subgraph, which is made of so I take, say, k nodes, say vi plus k, okay? And then I take the subgraph spanned by these k vertices, okay, with all the edges in between. Okay, this is my random subgraph. Okay? So that's what we take for dense graph. If the graph is not dense, and you take this model, you're not going to go very far, because most of the time this will be empty. Okay? In which case you switch to another model where you take a random node and you take the immediate neighborhood of that node. Okay?
K is constant.
K will be constant. So typically K will be 1 over epsilon. So it depends on epsilon. Okay? All right. So now comes the main definition. So let's put it here so that it stays. So what is an epsilon tester? So an epsilon tester is a randomized algorithm So an epsilon tester for class C is a randomized algorithm for C such that, okay, so if the input X is in C, then the algorithm, the probability that the algorithm accepts is 1. Condition 1, and condition 2, if X is epsilon 4 from C, then the probability that the algorithm rejects is bigger than, say, 2/3. Okay, so the probabilistic space, we have a randomized algorithm, so just imagine that we have two choices at every time, so we have a complete binary tree, okay? And you look at for a certain time, for a certain depth d, at what's the proportion of the leaves that accept and reject, okay? So if you have an input in the class, the probability should be 1, you should always accept in this definition. So this definition is called a one-sided tester. But then if you are epsilon 4, you should reject with high probability. So it's like saying here in this picture, you have, say, another, okay, everything to the right here is epsilon 4. And you have a gray area of the points which are epsilon close. And for the points which are epsilon close, you don't have any, you can say anything. Like you can actually make mistakes. Okay? So you don't guarantee anything in this area. And then, essentially, the third condition is the number of queries is a function of epsilon, but not of the, so the size of the input, say, is n, and the number of queries should not depend on n, depends only on epsilon. Okay, so that's probably the strongest definition of a tester. You can weaken it. So one way to weaken it is not to put 1 here, but to put, say, 2/3. Another way to weaken it is to say, well, number of queries, okay, maybe this is a bit too much here. Maybe even if I have a function, say, f of epsilon times log n, it's not bad. Okay, because I have only log n queries, so, you know, it's not so bad. Maybe log n to some power p is not bad either. Okay, but maybe square root of n, that starts becoming worse and worse. But still, square root of n is sometimes extremely useful. I mean, if n is a billion, square root of n is is a lot less, right? It's like around, 50,000 or something like this. So that's a way to weaken it. But of course, to understand the idea, best thing is to think of number of queries as constant, depending on epsilon. Okay, and of course, when it depends on epsilon, if a good tester is, for example, if this number of queries is 1 over epsilon, or 1 over epsilon square, but you have sometimes tester where it's 2 over 1 over epsilon. That becomes slightly problematic, okay? Because, say, epsilon is 10%, so well, if epsilon is 10%, this is still kind of manageable. But if epsilon is 1%, okay, then this is totally out of scope. Okay, so that's the difficulty. But let's let's work with the easiest of these. So just constant number of queries. I accept with probability 1, and when I'm far, I reject with high probability. That's the best thing to do first. All right. So now, we're going to find some simple tester in a minute, but by far the most classical tester is the one on linearity. Just before I go to this tester, I need a last definition. What does it mean that a property is testable? Say a property C is testable. If there is an algorithm such that for all epsilon, it is an epsilon tester. Okay, in other words, it's the same algorithm for any epsilon. So I can, if I give you epsilon equals 10%, okay, you work with the algorithm. If I give you epsilon equals 10 to the minus 10, it's the same algorithm, just the parameters are different. Okay, so that's important. All right. So now, before we go to real words and so on and so forth, let's study the first example of essentially discrete functions. So let's suppose you have a function from 0, 1, n to 0, 1. So, okay. And what does it mean for f to be linear? So for discrete function, maybe I can write in blue. So if there is an a in 0, 1 to the n, such that essentially f of x equal a product x. So this means this is sum of the ai xi. Okay, so that's a classical dot product between two vectors. Okay, so let's suppose I take this as a definition of a linear function, and I claim that if I'm linear, then it does imply that for all xy, f of x plus y is equal to f of x plus f of y. Okay. Now, obviously, just what you just have to write a product x plus y. It's actually ax plus ay. So this is precisely what it means here. Now, as you may guess, the converse is also true. If my function is like this, then actually there is an a such that f to x f is actually the product of a times x. And you think about, trying to discover if f of 1 is 1 or 0, essentially, and then once you have this, you discover that the next one, and so on and so forth. And these two definitions are actually equivalent. Okay, so now, once we have functions, so obviously, let's introduce a distance. What is the distance between two functions? F of x, f of g. Well, okay, it's okay. Well, you can think of it as a probability. If I take a random x, that f of x is different from g of x, and it's also the number of position x such that f of x is different from g of x divided by 2 to the n. Now, if you don't like this ugly notation, then you take this set, and this is the cardinality of the set. Okay, so obviously that's a function.
Just a Hamming distance.
Hamming distance, if you want. Okay. Now, what is a query to a function f? Obviously, is I give you some x, and you give me f of x. So, which is 0, 1. One query. Okay. So, what we want to do is now to sort of generalize what we could do on a standard real, for example, where you have functions that are almost linear. Okay, so for example, if you're on a real, okay, well, this is a function, linear function. Now, this is quite far from a linear function. Now, this is it far or is it close to a linear function? Well, let's see this in a minute. Let's see first an example of a function which is okay. So here on this point, I have totally crazy values, but on the rest of the function, I'm pretty okay. Then what is the probability that f of x is actually the same as g of x for a linear function g? Well, it's going to be high here on the yellow curve. Now, this curve, of course, is going to be far from any linear function. What about this curve here? Is it far or is it close?
Far.
It is far. Okay? All right. Okay, that's not quite obvious, but okay, that's a natural thing that we want to do. So now, so in a way, what we want to do is to generalize this correspondence to something, to functions that are close to being linear. So if I'm close to be linear, I can imagine this test, or I can imagine this test. But obviously, what I'm going to do is imagine this test, okay? And this is called the BLR tester. Now, BLR, roughly in the 90s. Now you have three famous authors here. You have Manuel Blum, Mike Luby, and Rubinfeld. And actually, this paper is way before the theory of tester. It was like maybe 10 years before, okay? And so what is their tester? Is essentially applying this test. So now, imagine that you take a random x, y, then you compute x plus y, and you check three queries. Do I have f of x plus f of y equals f of x plus y? Okay, I need three queries to do this. Right? All right. If f is linear, it means that f of x is like a times x, and by what we saw, the test is true. So this will always be true, probability 1. So I check this condition. And now, if f is far from being linear, I have to prove that this test will fail with high probability, with probability 2/3. Okay? And this is, of course, the hard part, and this is somehow the beginning of the subject. Okay? So how do you prove that if f is far from being linear, this test will fail with probability, large probability? Okay, so this, when actually Blum, Luby, Rubinfeld worked on this, they didn't use Fourier analysis. The Fourier analysis came much later. And this is today the standard technique that we use for several reasons, because it's somehow beautiful and extremely useful in other contexts. Okay, so it can be, it's one of these techniques that you should have in the back of your mind. You can reuse it, certainly. Okay, so that's why I think it's interesting to spend a bit of time on it. Okay, so that's what we do now, before we move to the more realistic tester in practice. Okay, one last thing on the motivation is why has it become fashionable today to have testers? Okay, now suppose I'm sure you're aware of this big data phenomena, which is quite true, is that you can turn to any social networks, they send you this huge data. But one of the characteristics of this data is that it's not perfect. They tell you there's a lot of errors, okay, in this data. So what can you do with this? And first of all, how would you model the errors? Well, one way to model the errors is to use the distance that you have here. Okay, so if you have an input W with error epsilon, so I'm going to write this incorrectly somehow. It means it's a word W prime, such that the distance between W and W prime is less than epsilon. Okay, so I have 10% noise. 10% noise on social networks it's nothing. It's more like 30%. Okay, you have 30% noise. All right, so what do you do with data that are 30% noise? Okay, if you ask for any property of these data, 30% noise, so you're going to get a property of W prime, which is what you observe. But can you infer a property of W? Okay, that's the real thing. And that's where testers come in. Why do testers come in? Because essentially, imagine that I take this epsilon to be twice this one. Okay, so let's call this one epsilon prime. And so I'm running my tester on W prime with this epsilon twice the noise. Okay? So I'm asking, okay, is W prime 2 epsilon far from the property? Okay? And if it says yes, okay, you're far, in the sense that it answers negatively on the test, it means that this guy is at least epsilon far from the property. Okay? Because this one is only, essentially you have distance 2 epsilon, so this one is necessarily further than epsilon. Okay? Because the noise, could add or could subtract, but, there is a relationship between the two. So in other words, if you have very noisy data, essentially anything you can do is a tester. I don't think any practical method that can say anything meaningful. If you have a lot of noise, and of course you don't know where the noise is, this is the basic hypothesis. So that's why if you're reading data on social networks, all you care are for testers. You don't really care for exact algorithm. You don't care about exact algorithm. You go for algorithms that really make a shift. Either you're for or you're satisfying the property. Okay? And that's why these algorithms are becoming essentially the engine on big data. I would say like this. Okay? Another connection is that the original paper, which I should have mentioned by Goldreich, Goldwasser and Rowan, around 98, called, it has in the title Testability and Learning Properties of Graphs. Okay? So there is a very strong connection between the learning and the testability. Okay? Because actually, when you learn, what you're trying to do is actually compute a certain property that is testable, okay, to differentiate between two classes in this sense. Okay? So there is strong connection both in the learning world and in the big data world. But the big data world is more natural. All right, so that's for the motivation. So now let's switch to what we want to do. And let's go to the basics of the Fourier analysis. Okay, so let's see, where is my eraser? Here. So what do I erase? Maybe erase this. Okay. All right, so first thing is a change of notation, is that instead of looking at 0, 1 to the n, I will be looking at -1, +1 to the n, and then the function into -1, 1, +1. Okay, so it's historical, and essentially you can think of mapping 0 into 1 and mapping 1 into -1. Okay, in which case plus is going to map into multiplication. Okay? If you look at the adding table modulo 2 of 0 and 1, and the multiplication table of 1 and -1, they match totally. Okay? So this is the first thing. And then what is the Fourier expansion? So now what is a linear function? A linear function is essentially the sum of the xi, and now a linear function is going to translate into a function like this, which is a product of sum of x sub I for I in S. Okay, so for example, if S is, say 1, 3, then key S of X is X1, X3. Okay, first bit and third bit. All right? Now, these are the linear functions, and now the magic is that I can decompose any function on the basis of the set of linear functions. So I can write f of x as sum over s of a coefficient, which is called the Fourier coefficient, key s of x. All right, so that's okay. So essentially, any function can be decomposed on the basis of the linear functions, and you write it like this. This is the coefficient of the on S. So, for example, if you want to see an example, imagine the function mean on x1, x2. Okay, what is its expansion as a Fourier on the Fourier basis? Well, it's actually this function. Okay, so the important thing is that the coefficients here are real. Okay, they are not minus 1 plus 1, they are real. Okay, so the decomposition is the following: x1 over 2 plus x2 over 2 plus x1, x2 over 2. Okay, so you can guess if you put, say, minus 1, 1, what is the minimum between minus 1 and 1? It's minus 1. So this is going to give you minus half. This is going to give you 1/2, so it will cancel out. And this will give you minus 1/2 plus minus 1/2. It will give you minus 1. Okay, so the coefficient for the empty S is minus 1/2. For S equal x1, it's 1/2, and so on. Okay? Take your favorite function on n bits, you have a unique Fourier transform. Okay? So just a bit of history. Do you know, so Joseph Fourier? Maybe you never heard of him? Okay, so he lived around 1800. He could have visited St. Petersburg, but I think he did not. So he lived in the times of Napoleon, and he invented this Fourier transform, but of course for continuous function. Okay, the discrete Fourier analysis was done much later. And as I said, if you like logic and you like non-standard models, there is a way to lift this domain into a non-standard, with a non-standard n here. So you will have actually infinitesimals, and thanks to the infinitesimals, you can get the classical Fourier transform as a discrete on a non-standard domain. It's very elegant, quite interesting, and okay, so just for those of you that like mathematics, it's an interesting topic. All right, so what I want is to prove now in my context this. Okay, so I want to show that, so the goal is f is epsilon 4 from being linear. So let's call the class of linear function L. Okay, so if L is epsilon 4 from L, then the probability to not pass the test should be big. Okay, so the probability that f of x plus now plus is multiplication, f of y is big. Okay, notice that here I keep the notation x plus y. I should say xy. Okay, but but traditionally to really separate the two, now the function, the plus becomes multiplication here, but I keep the plus, although it's a really multiplication. So that's what I want to show. And one way to prove this is actually to prove the contraposition. In other words, what we're going to prove is that if the probability to fail is large, okay, so equivalently we could prove the following thing. If the probability that I fail okay, so I want the negation of this, so the probability that say f passes the test is bigger than 1 over epsilon, then f is epsilon close. Okay, so it's not quite a contraposition because I'm playing a little bit with the constant. But, okay, so here just imagine that this is A implies B, and now I'm saying that not B implies not A. Okay, so not A means not epsilon far, means epsilon close, and not B means the probability of this event, which is, okay, because I reverse this. Okay, this is 1 minus the probability to pass the test. Okay, so therefore, if I prove this, that amounts to proving the goal. Okay, that will turn out to be slightly easier. Okay, so that's what I want to show. Now to do this, I need the basic of the Fourier analysis. So maybe I can do a couple of lemmas here. So I need 5 lemmas, but they essentially, some of them are very easy, and that gives you the spirit of the Fourier analysis. And once I have this, then that will become very easy. All right. So first, a definition. What do I write as fg? Like a scalar product of 2 vectors. And by definition, is going to be the expectation of f of x, g of x, which is also equal to the sum over x of f of x, g of x, divided by 2 to the n. And that's the definition of f dot g. All right. So now, first lemma. If I take 2 base functions, key s and key t, remember key s is this linear function, key t is the same thing with a different subset. Okay, s and t are subset of 1 n. Okay, so key s, key t, what is it equal to? Well, it's equal to 1 if and only if s equal t, and you know, so 0 otherwise. All right. So why is that? Well, just evaluate just evaluate the previous definition. Okay, so you're going to get sum of the key s of x, key t of x over x divided by 2 to the n. Okay, now when s and t share some elements, essentially you get the monomial square. Okay, so if I is in s and I is in t, then out of this you get xi square. Okay, so xi square, it's always 1. Okay, so if s equal t, essentially all the elements are equal to 1. So this is going to be 2 to the n. So then you get 1 here. Now let's suppose s and t are not identical. For example, there is an I for which I belongs to s, it doesn't belong to t. So essentially what you will get in this product is some xi. Okay, and then the other elements square. Okay. Well, so the elements that are in both sets, they are square, otherwise the elements is not square. Okay, so suppose you have 1, which is not square. Then you have the sum here over 2 to the n. And you have as many, essentially, sometimes this is 1, sometimes this is minus 1, and you have as many monomials with monomials with minus 1, so the whole thing will be 0. Okay, so if s is different from t, then the product is 0. All right, which is the basic, essentially, it means that we have an orthonormal basis. All right, now, what is f of s in the decomposition? Well, it is the same as f product key of s. Okay, why is that? Well, we just apply the definition, and it's going to be sum over x of f of x, key s of x, over 2 to the n. But then this f of x, you use this definition, and then you will have key s here, that will multiply with this one. Okay, so let's call this key t. Okay, and this will be essentially, I use the previous notation, so this will be essentially f of s times key s plus f of s times key s key t for s different from t, but this is 0, so essentially we are stuck to f of s key s, but this is 1, so that's essentially the lemma 2. Okay? All right, so now just one remark is that this, it's also, imagine you develop this and you think more as a probability. Okay, so you can write it as the probability that f of x equal key s of x minus the probability that f of x is not key s of x. Okay? And by definition, this is a distance between f and key s. And therefore, the probability that f equal key s is 1 minus the distance. So this is 1 minus twice the distance between f and key s. Okay? So in other words, this coefficient the Fourier coefficient f hat of s captures the distance in a very direct way. Okay? That's good to know. All right, so I'm almost done. I need the third lemma. And you'll see that once we have the 5 lemmas, then this is going to go on its own straightforward. All right. And in some way, these 5 lemmas, they capture the Fourier analysis in the discrete case. So lemma 3, what is fg for 2 arbitrary functions? And this is, so if you know, if you're familiar with Fourier analysis, then you should know that this is f, the sum of s of f of s times g of s. Maybe you've seen this, right? The dot product of 2 functions is actually the sum of the product of the Fourier coefficients. Okay, so how do you prove this? Well, you write f of g as the expectation of over x of f of x g of x. Okay, then you use the definition here for f and g, and you see that you get the product of the coefficient when the 2s, when you have key of s for f and key of s for g. Okay, when then the key of s multiplied to 1, and when you don't have the same s in both development, then you get 0. So that's essentially the argument. So essentially that's a sum of s of f of s g of s times key s key t. Okay, and the only times this is not 0 is when s is equal to t by the previous lemma. Okay, so that's okay. Now I need 2 more lemmas. So what is f times f? Dot product ff. Now, I just apply this, so this is the sum of the fs squared, and of course it's also 1. Okay, because essentially you use the previous result. All right. So now, before we get to the last lemma, we need the definition of what is a convolution between 2 functions. So let's suppose I have 2 functions, f star g. So this is sometimes called the convolution of f and g. And by definition, this is the expectation of y of f of y g of x plus y. Okay, this is my definition. And now my last lemma, L5, is to say that essentially, if I look at the Fourier transform of f star g, okay, what can I say about f star g Fourier on s? Then essentially this is f of s times g of s. Okay. All right, so maybe let's skip this because it becomes a little bit, essentially it's just rewriting. You have to apply the definition of this will expand like this, then you replace, okay, so you apply this definition, and then you change variable, you introduce a new variable, x plus y equals z, and so on and so forth. You play a little bit. Let's assume, because it's it's not 3 lines, it's 4 or 5 lines, but it doesn't add up too much to the game. Okay, so let's assume this, and it's in the notes. So now let's finish the game. I have everything ready. Now I need to prove this. And I'm done. All right. So now, probability that f passes the test. So f passes the test, it means that f of x plus y equal f of x times f of y. Okay. All right, so I'm now I'm going to say that it is the same as the expectation on x and y of a complex expression, which is the same 1/2 plus 1/2 of f of x, f of y, f of x plus y. Okay, so why is it? Is that if the test is true, then this expression is 1. Okay, because f of x plus f of y is going to be 1. 1/2 plus 1/2 is 1. Okay, and if the test is false, this is going to be 0. Okay, because this is going to be -1. So 1/2 minus 1, it's going to be 0. So the expectation of this is actually the same as measuring this probability. And you can see that now I have the ingredients, okay, because I'm going to massage this a little bit, and I have everything. I'm going to apply this lemma, and the whole thing is going to fall. Okay, so that's... maybe I should erase this here. Okay, so I apply lemma 3, okay, to the product. So I suppose I have a product of two functions, this function and this function. Okay, so this is going to be the same as 1/2 plus 1/2 of the sum of f of s times f of s. This is the convolution. Now, this f of y, g f of x plus y, is the same as convolution of f and f. Okay, f convolution with f on x is the same as this. Okay, so I apply L3, and I get essentially the coefficient of this, and I'm going to apply now L5, and I'm going to get 1/2 plus 1/2 sum of the f of s to the power 3. Okay. All right. But then this actually is not very smart to do. It's better to do it like this: 1/2 f of x okay, so maybe let's write it like this: max of f of s times ff. Okay, so just imagine that this power 3 I decompose into f and then f to the power 2. F to the power 2 is this, which is 1. And then there is a coefficient which is maximum, right? So I can, essentially it's like saying you're factoring the maximum coefficient out, and then you sum and that's what you get. Okay? So then this is less than 1/2 plus 1/2 max of f of s for some s. So let's call it s star. All right.
So if you write s star, you can probably remove max.
This is a special. There is a special S such that the f of s is maximum. Maybe I shouldn't write it as star, but s as s naught. Okay? And now I'm going to use the distance. Where is my connection between the f and the distance? So essentially I have this is the same as 1 minus the distance to f, to the linear function key of s naught. Okay? Key of s naught corresponds to the coefficient f hat of s naught. Okay? And before we figure out the link between f hat and the distance, which is exactly this. Okay, so essentially I can rewrite so here we had 1 minus epsilon. Okay, so I multiply everything by 2. So this is 2 minus, so this is, so I replace this by this and multiply everything by 2. So I have 2 minus 1, 1 minus 2 epsilon, smaller than the f of s naught, which is 1 minus distance of f and key of s naught, and therefore that's what the distance of f and key of s naught is less than epsilon. Oh, this is 1 minus 2 the distance. Okay, remember 1 minus 2 distance was the coefficient. All right, so that's a conclusion. If the probability that I pass the test is large, then I'm close. I'm close to what? I'm close to the function, to the linear function key of s naught. Okay? So see, the demonstration here is quite simple. Is that this event, the probability of this event is the same as the expectation of this function, and we prepare everything so that now this I can replace by the Fourier coefficient. Then this I bounded by the maximum times
so
the f squared.
Over S0. The maximum is taken over S0.
The maximum is taken over all the s. So what is s naught is chosen such that it maximizes over s the f of s hat. Look at the coefficient which is the biggest among all. This is for a certain s naught.
Okay, but then you can remove maximum in this expression actually. Then you don't need maximum this yet, right?
Okay, because sorry, yeah. Let's exactly. Okay, maximum of this and okay, maximum of f hat. This is f hat of this. Thank you. Okay, now believe it or not, if you have seen the early proof of Bloom, Luby, and Rubinfeld, this was like 5-6 pages of probabilities, and sometimes there were mistakes and so on and so forth. And clear, as clear as possible proof using the discrete Fourier analysis. It's actually quite recent, and see everything falls naturally into the picture. So this technique is used in many areas where we look for lower bounds on the query complexity. Here we're not looking at the lower bound query complexity, we're just looking at, there is if I don't pass the test, then there is necessarily a high coefficient, and this high coefficient is actually it's going to reverse. So if I pass a test with high probability, if I pass a test with high probability, then there exists this S naught with a high Fourier coefficient, and I'm actually close to this function. Okay, and this is actually the function you look for. Okay, so think of the corrector, for example. You know, if I give you a function by queries, maybe my function is incorrect, but it doesn't matter. You're going to correct it naturally by looking at this linear function x of S naught. So it doesn't matter. Okay, so just before we take a break, let's move on to words. Okay, because this is nice. It's nice mathematically, and but then, okay, how can you use this in practice? All right. So let's suppose. So let's suppose let's erase this. Oh. So now let's go back to the real world. We have a word, Wn. Imagine a word of size 1 billion. Okay, and let's suppose you have a regular expression. Let's take a very simple regular expression. Say a squared b squared. Okay, so I have a's followed by b's. Okay. And now, imagine you have a noisy word. Okay, so a noisy word means edit distance. Okay, so what you observe is W prime, which is Wn plus some noise epsilon. Okay, so I'm asking you, okay, am I close or am I far from this regular expression? Okay, so what you can do is of course run on take the automaton associated with the A star B star, run W prime n with a word of size 1 billion. It'll take you an hour on a standard machine, but at the end, suppose it says no. What do you do? What does it tell you about Wn? Nothing. Okay, you have no clue of. Okay, I know there are errors, so the errors can be anywhere, right? I mean, so it could be that actually my word was perfectly the whole bunch of A's, then whole bunch of B's, but then because of errors, there is a B here, there is a B here, there is an A here, and A here. Okay, so your automaton immediately at this point it can say I reject. Right. So okay, but let's suppose the errors are concentrated at the end. Then at the end it's going to say I reject. But what can you say about Wn? Nothing. Okay. And now what I'm saying is that it's actually don't read the word. Actually, so the most stupid method to read the word is the worst. Okay, sample the word. Okay, so make a few samples. How many samples? Well, let's say K is 1 over epsilon samples. Depending on the epsilon you want for the tester. Okay, so if you suppose you have a noise, this noise is 10%. Which is quite big, right? Well, essentially I'm going to take K equal 1 over 2 epsilon, okay, which is think it's should be bigger. So 1 over epsilon is going to be 10. And well, actually, what I prefer to do is to make a k equals 20, something like this. Okay, so k is a number of these guys. But of course, it's you can also make samples of length k. That's a slight advantage. Okay. In this case, you don't need, but in general, you will need samples that are slightly longer. Okay? And what I'm saying is, so what am I going to check? Well, I'm going to check essentially, so for example, if I read A, B, B as samples, I accept. If I read A, B, I reject. Okay? So when do I reject? I reject when I see essentially BA as a pattern of successive samples. Okay?
So you mean, so you don't need to make them simultaneously, you can still make them one by one.
In this, because here the regular expression is very simple,
Right.
one sample, one position is enough. Okay? But in general, imagine you have a large regular expression here, which is much more complex than this. Then you will need a random position and then all the consecutive position for, say, a length k. Okay, k equals 1 over epsilon. So slightly more than one query, if you want. Okay? And what you're going to look for essentially is, well, that's what we're going to see, but essentially you're going to see, is this compatible with my connected components in my automaton and so on and so forth? Pretty much exactly like in this situation here. Here, your automaton has 2 connected components, right? The automaton is essentially an A followed by a B. Okay, well, let's suppose we have a B. Okay, this is my smallest automaton, right? So I have 2 connected components, this connected component, this connected component. Okay, so in general, when you look at an automaton associated to regular expression, then you may have several connected components, especially if the automaton is non-deterministic, you may have this situation, typically. Okay, here you have an initial state, okay, and actually if the automaton is non-deterministic, it's even nicer. Okay, so this is going to be the component C0, C1, C2, and C3. Okay, so let's suppose the final state is here, or all final states are here to make it simple. Well, essentially, I have 2 paths. So either I have the path C0, C1, C2, or I have the path C0, C3, C2. Okay, so it's pi 1, it's going to be pi 2. So what I will do is I will design a tester for each pi. Okay, so I'll enumerate the pi's, and then for each pi I will have a tester, and so on and so forth. Okay, that's what I want to sketch with you now. Okay, that's the idea. All right, so in other words, you have a very long word, you want to know if the word is close or far from a regular expression, but the word is noisy. Okay, then apply a tester, make a few samples, and that will be enough. And this is your best decision. Okay, in a particular sense that I will explain in a minute. Yes, so that's what we need to do now. So let's set the framework and let's have a break. So the framework is going to be the following. I will have essentially a tester for a connected component. So first I have a tester for a connected component C sub I, some epsilon. Okay, given a word W. Okay, and then after, so that will be tester 1, and then a tester 2. Essentially, I will have a pi, which is a sequence of connected components, so epsilon W sub n. And then I will have a tester 3, where here I have a regular expression, epsilon Wn. So I have to have a progression tester for connected component, then a pi, then a set of pi. Okay? That's what I will do.
So pi, what is
Pi is a sequence of connected components. Okay? Here I have pi 1, pi 2, and so on and so forth. Okay? So we have to start with this tester first. That would be the basic. Once you understand this one is easier to follow. And that will give us a tester for the edit distance. Okay? So historically, the interesting thing is that the first tester that was given for regular expression was for the Hamming distance. So it was given by Allen and a few other authors around 2000. But somehow the tester with the edit distance is much easier, much simpler. Okay? And generally it's always like this. The smaller the distance, the easiest is a tester. Okay? And this is something peculiar there. It's actually not so well understood why, if I have a set of distances that decrease, why is the testability so much simpler for some distances as opposed to some others? Okay, so that's a mystery. Now, once we have this, we will move to these visual push-down languages, or you can also think of trees, regular trees. Okay, so VPL, it's the same thing as regular trees. So it's very close to what is called in computer science data type definition on trees. And the magic is here we don't have testers for the edit distance. The only testers we have are square root of n testers. And now if you move to streaming algorithm, then essentially you can get polylog n. So exponentially better. Okay, this is if I'm streaming, and this is if I'm not streaming. Okay, so that's essentially gives a motivation for the difference between testers and streaming algorithm. Okay, so that's what we do.
So square root n is for testers, you mean, so this is like...
For trees. Okay, the number of queries, given a tree that you want to know if it's close or far from a DTD. DTD is a representation of a regular of a tree automata, or it's a representation of a regular expression on trees, or you can view it in many different ways. But that's the right notion of a regular expression on trees. Okay? Essentially, you have nested words that are nested properties. Okay, so that's what I wanted to do, if you're interested. And then I can depending on the time, then after that we'll move to graphs.
So when saying for streaming, you say it is log n to the k, and this is, what is it, memory complexity?
No, it's number of queries. It's always query complexity. Okay, for tester, we actually do not count the time complexity. we assume that we do, you know, whatever you ask the queries, we only count the number of queries.
Right.
What you do after, we don't count it.
Right.
Okay? The reason being that if you have finely many samples, well, what can you do with this? You know, you can do maybe exponential in the finite numbers if you want, but that's still finite.
Yeah.
Okay? So, but there is something peculiar, I will try to explain why intuitively, that when I'm streaming, I need much less queries than when I'm not streaming. And somehow it's counterintuitive, and this is what I will try to explain. Okay? And now, if you want real situation with social network and so on and so forth, then okay, these ideas help a lot, and I believe they are actually the keys to handling big data. Okay, so that's is that okay to do a break? Okay, so I hope I'm not going too fast or I'm not going too slow. So if you want to remember one thing, remember this definition and the notion of a testable property. Okay? And of course, the Fourier analysis on the linear function is something that is has the advantage to actually you get exposed to this Fourier analysis on discrete domains, not quite obvious to handle. And then there is much to, I mean, it's a very useful technique.